We are moving right along and entering into Unit 4. Unit 4 is all about the ocean. We'll cover the ocean in 3 different chapters. This first chapter, chapter 13, looks at the ocean floor. And then we'll look at the dynamic ocean in terms of the living organisms that we find there. And then finally, in chapter 15, we'll take a look at how the ocean influences weather and climate and other events on Earth. So the Earth is known as the blue planet or the water planet because the ocean covers about 71% of the Earth's surface. In fact, all of the continents could fit into the ocean, in particular the Pacific Ocean, and have room left over. So really what we're looking at in these chapters is bathymetry, which is looking at the topography of the ocean and being able to map the different topographic features that we see on the ocean floor, as well as oceanography, which encompasses not just bathymetry, not just the geology, but also the chemistry, the physics, and the biology of the ocean. So now we're going to watch 2 smart figure videos, and I'll pause periodically throughout those to add a few details, but we'll look at the different oceans in the first smart figure video, and then in the second one we'll look at how we're able to measure all of these different topographic features that are on the ocean floor.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the relative proportions of land and ocean in the Northern Hemisphere and the Southern Hemisphere. So let's begin by taking a look at the 2 hemispheres. Here's the Northern Hemisphere up top. Our view of the Northern Hemisphere is centered on the North Pole, and you can see that the Northern Hemisphere is dominated by land relative to the Southern Hemisphere. So the Southern Hemisphere, in stark contrast, is dominated by ocean water. You can see that there's very little land down there. Obviously, the continent of Antarctica is front and center, but you can see there's also significant land in the Southern Hemisphere in South America, Africa, and Australia.
So looking at this picture here, you can see that the Northern Hemisphere, we see a lot of continent. We see a lot of land. So the Northern Hemisphere is sometimes referred to as the land hemisphere. And then we look at the Southern Hemisphere, we see Antarctica and then a few pieces of Africa, Australia, and South America, like he mentioned. But the rest of it is all water. And so sometimes the Southern Hemisphere is referred to as the water hemisphere.
Africa and Australia. Here's a different projection of the surface of Earth. You can see here the Atlantic Ocean is prominent, and then over on the far left and the far right is the Pacific Ocean. And we also have the Arctic Ocean, which is up towards the North Pole. We have the Indian Ocean between India, Africa, and Australia.
So here you can see the 4 oceans we learned about in social studies when we were kids. So we have the Pacific Ocean, which is the largest and the deepest of the 4. We have the Atlantic, which is about half the size of the Pacific and not as deep. Then the Indian Ocean, again, smaller than the Atlantic, but about the same depth. And then the Arctic, which is less than 10% the size of the Pacific and only about a quarter as deep as the other 4 oceans.
And then lastly, there's this sort of arbitrary ocean down there at the bottom called the Southern Ocean. And the Southern Ocean is really just an extension of the Atlantic, the Pacific, and the Indian Oceans. However, it's sometimes worth considering it as a separate ocean body because it's surrounded by these currents, the west wind drift and the east wind drift, which end up isolating Antarctica from the rest of the world ocean. That's one of the reasons that Antarctica is so cold. So what we're going to do now is we're going to go ahead and slice down through the different latitudes. So we're going to cross basically the equator and 30 degrees latitude, both north and south, and 60 degrees, and go all the way to the poles, north and south. And we want to see basically how much land and how much ocean there is at each of those different latitudes. That's what this figure shows. So basically, the brown portion of the figure on the left is showing how much land there is at different latitudes. So you can see the 0 degree mark there in the middle is the equator, and then basically north and south of the equator, you can see there's a big discrepancy in terms of how much land there is. Most of the land is in the northern hemisphere. On the right side of the figure are these different blue-colored areas, and these blue-colored areas represent the proportion of different ocean water that exists. So the Atlantic is that body right there. Then up above at the top, we've got the Arctic Ocean. Then there's the Pacific, which is the biggest of all the ocean bodies. And then lastly, the Indian Ocean. What latitudes on Earth have no land whatsoever? Well, in this figure you can look and you can notice that up here at the far northern extreme of Earth, there is no land up by the North Pole. And then there's also a small zone basically between South America and Antarctica where there's just open ocean as well. This is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at various techniques of exploring the ocean. And after watching the video, you should be able to describe each of those techniques and how they work. So in the olden days, oceanic exploration was done by means of a very simple piece of technology, a rope. And that rope was lowered over the side with a weight on it, and basically when the rope went slack, that meant that the weight had touched bottom, and it gave a rough indication of how deep the bottom was.
So this image that you're seeing here on your screen is the HMS Challenger, which was a British exploration ship. It departed England in December of 1872, returned back home in May of 1876. So it was a 3.5-year journey that took them across 79,000 miles. They traveled to every ocean except for the Arctic. And in addition to trying to measure the depth of the ocean, they also were checking salinity and other properties. They made the first recording of the deepest known point on the ocean in 1875, and this spot was later named the Challenger Deep in honor of this voyage.
So that works fine, but you're limited by the length of your rope, and it's not a very robust technique. A more effective way of figuring out what the shape of the ocean floor looks like is to use sonar.
So sonar was developed early in the 20th century. Sonar stands for sound, navigation, and ranging.
Basically, sonar is taking sound waves, bouncing them off the bottom so that they come bouncing back up towards the ship, and basically timing how long it takes for the sound waves to go down and then come back up. How long is that round trip? Because we know the speed of sound through water, we can then estimate how deep the water is. It actually can get even more precise than that with multi-beam sonar, where very precise pulses of sound are fired either from a boat or from a little device that's towed behind the boat.
So here you see two different types of technology. The first one here, the side scan sonar, or referred to as a towfish, this was developed after World War II by the Navy. The Navy was trying to find any torpedoes or other explosive devices that were left in the shipping lanes that might have been deployed by, enemy submarines during the war. This was able to provide some images of the ocean floor, but it wasn't that accurate at providing valuable information about the depth. So it worked for producing images, but not so much for depth. In the 1990s, multi-beam sonar was developed, and you see here that instead of it being one beam of sound waves being sent down at a time, it's multiple. And this type of technology allows the survey ship to map the features of the ocean floor along a strip that could be tens of kilometers wide. So this allows them to do, basically more scanning in less time. However, scanning the ocean is a very time-consuming task. These ships have to move very slowly to allow for proper scanning. And because of that, we've only surveyed about 5% of the world's oceans.
And we can end up getting really detailed pictures of the seafloor using this technique. For instance, here is what the seafloor looks like off the coast of Los Angeles and Long Beach, you can see the broad, flat, shallow continental shelf. You can see these little canyons that have been cut into the continental shelf, and then you can see the continental slope and rise down.
So here you see a relief map, but what's interesting is you notice these different contour lines very similarly to what we would find on a regular terrestrial topographic map.
Below that. The detail is quite extraordinary. We can actually even measure how deep it is to the ocean bottom without ever going close to the ocean. Satellites orbiting the Earth can pulse radar off the sea surface. So in this case, the purple little pulses are coming down, the orange pulses are going back up and being recorded by the satellite. And these record very slight anomalies in the surface of the ocean. So when you actually have mountains underneath the ocean, those mountains have mass, and that mass gravitationally attracts water to it. So you actually get very slight variations on the sea surface itself that correspond to bottom features. Finally, we can go even beyond the bottom by doing seismic reflection surveys. So here you basically set off an explosion, kabang. That explosion sends various seismic signals down to the bottom, and they actually penetrate into the bottom some distance, and then they come back up and are received at some sort of a receiver. Using this, you can actually end up getting profiles like the one seen up here on the top of the screen, where you can actually see the volcanic bottom of the seafloor, and then also you can see the sedimentary layers that have been draped on top of that. So you can actually see where you're likely, for instance, to find oil and other key resources.
So with all of this mapping that we've done, we've been able to discern three different types of topographic units on the ocean floor. We have continental margins, the ocean basin floor or the abyssal plain, and mid-ocean ridges. You'll see some of these on pages 412 and 413 in your book, some different features that we can find, and we'll discuss a few of these in more detail later on, some of these specific ones. But we will cover each one of them and how they form also. And the first one that we have are the continental margins. So I'm going to show another smart figure video on continental margins and have you see the difference in these active and passive margins and the different features that we can get as a result of those.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to distinguish between active and passive continental margins. Continental margins are the edges of continents, so they may be also the edges of tectonic plates, or they may not be. In the example of the Atlantic Ocean, the edges of the continents do not coincide with the edges of the plates, and so you have a very distinctive morphology to the seafloor that speaks of the lack of tectonic condition. If you look in detail, for instance, at the east coast of North America, you'll find that there's a flooded portion of the continental crust, which is called the continental shelf. And then offshore of the continental shelf, after the shelf slope break, there's the continental slope. So that's where there's this sort of sudden change in water depth. And beyond that, there's a gentler slope called the continental rise that leads to the abyssal plain in the deepest part of the ocean. You'll notice that notches have been cut into the continental shelf, and then running down those submarine canyons are turbidity currents, which deposit deep sea fans or abyssal fans.
So what you see here is a passive continental margin where we don't have two tectonic plates that are coming together. And you'll see some distinct features associated with this. So these are geologically inactive. They are sites where we have a lot of sediment that's going to be deposited. So we have up here the continental shelf, this portion that looks fairly horizontal, but it is sloping, just very slight, about 1/10 of 1 degree. So it appears horizontal to the naked eye, but there is a gradual slope. And then we actually get to the continental slope, which is very steep. This is what's marking the boundary really between the continental crust and the oceanic crust. And the slope here is between 5 and 25 degrees, depending on location. Then we have this little kind of continental rise here, that's a more gradual incline. It can extend out into the ocean for hundreds of kilometers. This is basically the accumulation of sediment that is coming off of the continental slope. Most of the sediment is deposited by these submarine canyons and these turbidity currents like he mentioned. So these submarine canyons are very deep, steep-sided valleys in the continental slope, and they may extend all the way across the continental rise out into the abyssal plain. And they have been basically excavated by these turbidity currents. These turbidity currents create this downslope movement of sediment, and basically they become dislodged and form kind of this slurry, almost like mud. And this is going to be pushed outward into these fan-shaped structures here. And these are called deep sea fans or abyssal fans. And they this is erosion. We talked about weathering and erosion a few chapters back, but this is just an example of erosion, except instead of erosion on the terrestrial surface, we're actually eroding the continental shelf and the continental slope here.
Those canyons and those fans are linked in terms of how they form. But that's about as much action as you're likely to see on a passive continental margin. If you go to the Pacific instead, you'll notice that the Pacific is much more active. There's lots of subduction zones happening around the Pacific. You'll recall that subduction is where more dense oceanic lithosphere gets shoved down underneath less dense overriding lithosphere, which in this picture is continental lithosphere, but it could also be younger oceanic lithosphere. If the subduction angle is relatively shallow, you end up getting a relatively shallow trench, and you scrape off lots of sediment and seamounts and things like that to produce an accretionary wedge. If the subduction angle is steeper, you can end up getting a deep trench, and you can get subduction erosion, where bits of the overriding plate are actually scraped off and carried down to the deep. Okay, so here's the Mariana Trench. This is not an example of a continental margin. We're just looking at oceanic crust here, but this is the deepest spot in the world ocean, the Challenger Deep portion of the Mariana Trench. Is this likely to be shallow subduction or steep subduction? Well, hopefully you said steep because it's really a deep trench, and deep trenches are typical of steep subduction.
So we took a look at our continental margin. So the second thing we're going to look at now are deep ocean basins. This is between the continental margin and those mid-oceanic ridges. These deep ocean basins make up about 30% of Earth's surface. They're very long, relatively narrow. They encompass the deepest parts of the ocean. Most of them are in the Pacific Ocean, but we do have some in some of the other oceans. Like you saw in the last video, the Challenger Deep portion of the Mariana Trench has been measured at 36,000 feet below sea level. So that is the deepest known part of the ocean. There's a picture in your book on page 417 of James Cameron, who was the director of Titanic and Avatar, among others, and he actually took a vessel in 2012 to the bottom of the Challenger Deep Trench. So they don't, make up about, like you said, about 30% of the surface, but they are significant geologic features because this is where we have plate convergence. The pieces of the oceanic lithosphere is subducting and going back into the mantle. So we have earthquakes that are associated with this as the plates scrape across one another. We also have volcanic activity, and we can get the development of a volcanic island arc. The Mariana seamounts are associated with these. We can also get continental volcanic arcs, such as those that make up portions of the Andes and the Cascades. What are some features of our deep ocean basins? Well, we have those abyssal plains, which are very deep parts of the ocean. They're incredibly flat. Your book mentions that they may be the most level places on Earth, and they are formed from thick accumulations of sediment. There are 3 types of sediment that can be accumulated here. We can have sediments from land that are transported out to the sea by wind or ocean currents, or even those turbidity currents coming off of the continental shelf. We can have mineral matter that has precipitated out of the seawater and dropped to the ocean floor. And we can have the shells and skeletons of microscopic marine organisms. And we'll talk about those 3 types of sediment a little bit later on. We can also have seamounts, which are submarine volcanoes. They can rise, of course, hundreds of meters above the seafloor. It's estimated that there are more than 1 million of these seamounts, these underwater volcanoes. Some, like the Hawaiian seamount chain, formed over volcanic hotspots. Some are near oceanic ridges. If the volcano grows large enough before it's carried away from its magma source, then we can actually get these volcanic islands. The Galapagos, the Canary Islands, and the Canary Islands are where the La Palma volcano is located, and that is still erupting. So it is still located over a volcanic hotspot. Then we can also get geos. Geos are submerged flat top seamounts that are formed when these seamounts that basically come up to the surface become inactive, and over time they're weathered and eroded away, and as they're carried away from their that volcanic hotspot, that volcanic activity, then there's no longer any new land being added to it, and they essentially just kind of weather away and sink below the surface. And then we can have oceanic plateaus, which resemble the lava plateaus that are composed of flood basalts, and these just come from outpourings of fluid basaltic lavas.